Hello friends, last time we had seen basics of signals, the representation of the signals, also what are the different properties of the signals. Now let us move on into the same topic. See, if you want to classify discrete types of systems, what are the types? Like there are static type of systems, dynamic systems, you have causal systems, you have non-causal systems. There are varieties depending upon the applications and uh, the signals. We can classify them in different types. So let us start with first as the static dynamic systems. Now what do you mean by static system? Those systems wherein the output depends only on the present input, then only it is called a static. For example, you cannot have an output wherein the input has been like the delayed input or the past inputs, you can say the future inputs. These inputs, if they are available, if the output is needing these inputs, then the output obtained is called, or the system is called as a static system. If the system is depending upon the past inputs, the future inputs, the present inputs, then it is called as a dynamic system. That means dynamism requires some memory, whereas a static system will not require any memory system. It's called as a memoryless system. Now going on to the further part, these are some examples. So x of n, see the n here required is, if I want to find a yn, if I want to find yn, I will require only those values of n which are presently available. See, for xn, if n equal to 0, so if I want y of n is equal to 0, y of 0, I need a value of x of 0. If n is equal to 1, that means I need a y of 1 to get y of n. So present value of input will give me present value of output. So here when I go for the second type of signal, it's so probably can take a of n minus 2 in n minus 2 or x of n minus 2. Here if it is x of n minus 2, here when n is 0, when y of 0 is required, when I want to have y of 0, I require a value of x minus 2. This is the requirement. That means I want the past values to obtain my y of 0 instance value. So this is called as a dynamic system. So here also, whatever is a present value, only you will obtain as a y of n. So that's why it is static. Here I require, suppose n is 2, I will require to have y of 2, I will require y of x of 4. So this is a dynamic system. Similarly, this is static and this is a dynamic system because I have combinations of present, the past and future values. So this is the requirement of the system. That's why it's called as a dynamic system. Now time invariant and time variant systems. Time variant is that wherein if input changes, the system also changes its output. So it's called as a time variant. And if this is not happening, when if the input is changing but still the output is not changing, that means it's called as time invariant. Now when you are having time variant, there is nothing is fixed. So what happens is there is no mathematical analysis for this. So that is the beauty of having a time variant invariant systems, where invariant systems can be best explained by the impulse responses, their frequency responses, transfer functions. You can have the Fourier domain in this. So all the operations can be done and the systems can be better explained than compared to the time variant systems. Also, we can have an example like if it is a rainfall per month, if I want to have, it's very time variant. We can't guess. Again, the noise effect, we don't have any control in the noise. But in the thermal noise and electronic components, it is time invariant. So we don't have, this is always there. It's, even if it is changing, this is going to be there. So another example is printing documents by a printer. Okay, so that is what the time invariant and variant means. I have a linear and non-linear system. So everybody likes to have a linear system because it is easy to operate, and non-linear systems are not preferred many times. So how do you define a linear system? Suppose I have a system with two inputs, 1 and 2. Okay, the multipliers, the scalars are a1 and a2. I can get an output as an operator. T is called a operator. Any operator, it can be a mathematical operation, like can have multiplying or whatever, any operation, yes, log or science, anything. So this is operation on the sum of the weighted sum of inputs, like a1 x1n plus a2 x2n. Now if I'm operating on the sum of the inputs, I'm getting some y1 yn. Now here the situation is a bit changed. Now there are two systems. X1 will give an individual output multiplied by A1 will give me 1 Y1n. Similarly, X2n will give me an output multiplied by A2 will give me Y2n. So Y1n is ready separately, Y2n is separately ready. Now I get the output. That means here, if the system is linear, then both the outputs should be same. This is called as a superposition theorem, wherein you can see in the next slide, the response to the system to the sum of the signals is equal to sum of the individual responses of the system. See, sum of the individual, this is one response, this is the second response. So this, if I try to add, it should be same as the response to the addition of the signals. So this is called as a linearity property. Some of the examples, you can see that this exponential always gives you non-linear systems. Square also gives you non-linear systems. An additional of constant also gives you non-linear system. Cosine of a signal will give you non-linear. Even if you take a inverse of x of n, x of minus n, you get linear system. Any logarithmic also is a non-linear system. Now getting into the causal and non-causal systems. When a system is said to be causal means it is said to be causal only when the system is depending on only the past and present inputs. This is a bit confusing, but we have to keep it in mind. Depends only on past and present and not future values. When it is depending on future, it is called as non-causal. Okay, so just see here, I can have x of n, x of n minus 1, these are all past values. So here these are causal. Now whenever it is the system is bearing an input called as x of n plus 2, it is called as a non-causal system. So it is requiring a future value. The examples are real-time DSP systems, and here is offline systems. So whatever I have discussed prior, it has been shown in this slide. See, we can see here, this is a present input, this is the past, so it's causal. Obviously this is causal. Here it requires a future input, so it's a non-causal. This is a causal. Here it is non-causal. Why? Because if n is equal to 1, if n is equal to 1, y of n, y of 1 will be equal to x of 2. See, it requires a future value. So this is a non-causal. Now this is all combination, that's why it is a non-causal. This is the way you define the or determine the system to be causal or non-causal. Stability and unstable systems. What is a stable system? A system is balanced input, balanced output, stable if every bounded input produces a bounded output. That means the input should be summable, output also will be summable in that case. If it is not, it is called as an unstable system. Now input is bounded means it is having finite, means it should be of such a value that it should be less than infinity. Similarly, the output will be less than infinity. That means it is going to be a stable system. So this is written in the words here. For stability, it is very important that the condition of balance input, balance output is obtained. System will be unbounded accordingly if you have an unbounded input. I can go for some examples. Just see some examples here. This is going to be bounded. This is going to be bounded input is there. Bounded. See, when I have a multiple of this makes it unstable. So that is the reason why it is unstable. So this is what the stability of thing is. Thank you.